So, before I start today's lecture, there is a point which I need to clarify, because some of the students were asking me after the class. It might have created more confusion. So, I just wanted to clarify that point. If you have an action for a system and if you have a way of defining that sum over exponential IA, then you get a propagator. Now, this you can do for lots of systems, okay? Not for all, because you don't know how to define the sum, but for lots of systems. In particular, you can do this for a non-relativistic particle in a potential. You can also do this for a relativistic free particle. There is no problem, you can do that. Once you have that propagator, you can go and check whether it satisfies the transitivity property, which I told you, that is G1 to 2, G2 to 3 should give me G1 to 3. Okay? This may or may not happen, because you already defined your propagator and you already computed it. It is not assured that this will happen. So, if this happens, then you can have a wave function and you can have a very nice interpretation for the wave function, and various things will happen. This is what goes on in non-relativistic quantum mechanics. In relativistic quantum mechanics, if you try to attempt to create such a thing with a single particle and all that, what fails is not the computation of the propagator. You can compute the propagator, but its interpretation is very, very different. Why is it different? Because that propagator will not satisfy this transitivity property. So, there is no notion of a wave function for a relativistic particle. There are approximate notions, but there is no precise notion. That is because a particle is not a localized agency in relativistic quantum field theory. And I pointed out to you that this can happen because of various reasons. At this stage, when I say that there is no wave function, there is no wave function because the transitivity does not hold. But then I also argued for you why this transitivity does not hold in relativity, but it holds in non-relativistic case. That is because in non-relativistic case, you can define the sum over paths in a particular way where only the paths which go forward in time is taken into account. Then by that very definition of the sum over paths, transitivity will hold. You cannot do this in relativity, maintaining Lorentz invariance and various other nice properties, because you need to accommodate particles which go both backward and forward. So, up to this point the logic is clear. Then you say that, look, if a particle is going backward and forward, in the intermediate time the number of degrees of freedom has gone up to infinity. So, you want to be able to describe the particles in terms of some other dynamical variables. The dynamical variable changes. It is no longer the position and momentum, but instead you have a system which has infinite number of degrees of freedom, which is a field, and then you take that field and then use that field to describe this, and the particles come out as excitations of the field. This is how the entire particle physics is done, and quite a lot of condensed matter physics is done. So, I want to describe that part to you today. So, in order to do that, I need two results. So, let me introduce those results. I expect most of you to have at least a noding acquaintance with it, otherwise you have to just accept it. Many of you will have. So, to do that, I wanted to consider a simple system, the favorite system of physicists, and some unkind people will say the only system which physicists can solve, which is a harmonic oscillator. So, the harmonic oscillator has a potential V, or rather let me write down the action which is integral dt of a Lagrangian. I will take the mass of the particle which is doing the harmonic oscillations to be 1. So, if it is half, let us say x dot square, one dimension, minus half omega square x square. So, the potential is quadratic. So, if I draw the potential, it is like this. This is x and this is V of x, and V of x is a quadratic with a minimum at the origin. So, if you put a particle here, it will come here, it will go up to the same level, and then it will keep oscillating. So, if the particle has an energy E, it will just oscillate between these two classically. And the lowest energy state is sitting here, where x dot is 0 and x is 0. Now, such a state is forbidden in quantum mechanics, because that means you have specified both x and x dot. So, the lowest energy state in quantum mechanics will have some amount of energy, and in fact, all the energy levels of this system come out quantized in quantum mechanics. So, in quantum mechanics, you could have written down the path integral, you can actually sum it for this case, but we have also found that you can have an equivalent description in terms of Schrodinger equation. So, if you do it using Schrodinger equation, I h cross psi dot is equal to minus h cross square by 2 because m is 1, d square psi by dx square I will replace by psi double prime, then the potential is half m omega square x square psi. Okay. And in particular, you are looking for solutions where this is a constant, that is, you are looking for solutions where psi has a time dependence which is e to the minus I e t. So, this is some energy value times some function which depends on E and x. So, there is an ansatz and you can put that in and the left hand side will become E psi. Then it turns out that these energy levels are quantized and they are equally spaced, and the nth energy level is given by E n equals h cross omega into n plus half. Now, is there anyone who hasn't seen this before? Just put up your hand. Good. So, everybody knows that harmonic oscillator energy levels are quantized. They are quantized in terms of integers, and n is equal to 0 is the ground state that has an energy half h cross omega. Now, you can one more, this is one result I need. One more result I need is the form of the ground state wave function, okay, the lowest ground state. So, the ground state of course is going to be sort of classically it is going to be here. So, quantum mechanically it is something which is peaked around that point, it is a Gaussian. So, the ground state for this system psi naught is proportional to, so there is some normalization constant which we do not have to worry about, exponential minus half omega x square. In fact, none of this is needed except that it is proportional to omega and there is an x square, the constants are not so relevant. So, these are, are there people who do not know this result? Just put up the hands. Okay. So, you can, even if you do not know, it is very trivial, you just have to plug it into this and you will find that the result follows. Okay. Just with this minimal amount, I can take you to quantum field theory and particles being excitations of fields and things like that, because that is a logical conclusion to the set of lectures. Yesterday, we showed that there is a bit of an issue that if I take a single particle and I work with it, I run into a problem. I need a system with infinite number of degrees of freedom in space and time, and that system has to somehow appear as particles at some level. Okay. This is magic, and the question is, how does this work? And it works only when you bring in relativity and quantum mechanics in a particular way. So, I wanted to show you that. So, I could have taken electromagnetic field, and electromagnetic field we already said is a bunch of harmonic oscillators, and work from that. But I want to do it in a reverse direction, and in a reverse direction it is a little easier if I forget that electromagnetic field is a vector, but I just describe a field which is just going to be a scalar. Okay. So, it is, you can think of it as one component of the electromagnetic field, nothing much will go wrong. So, the way I want to do that is that I want to start with oscillators and build for you a field. So, let us do it step by step. I have got one oscillator here, and I am going to add to it one more oscillator. There is an X oscillator, I am going to add to it a Y oscillator. So, the full Lagrangian is going to be half, there is an X dot square to which I am going to add a Y dot square, then minus half omega square x square plus y square. This is no big deal because these oscillators are not talking to each other, these are just two oscillators. Okay. So, first oscillator will have an energy level specified by nx, second oscillator will have a energy level specified by ny. So, any quantum state you are going to energy levels, you are going to specify by giving me two integers rather than one integer. Okay. The reason I do that is that I want to play a little bit of mathematical trickery. I want to introduce a variable which I will call q, which is just x plus iy. So, while x and y are real, q is complex. So, this can be written as half modulus of q dot square, because x dot square y dot square is just modulus of q dot square, minus omega square mod q square. Okay, this is completely elementary. So, now we will work with q, which is a complex oscillator. Now, suppose I have one complex oscillator, this is the Lagrangian. Suppose I have several complex oscillators, then the Lagrangian will be summation over, I will use the variable k to indicate each oscillator. So, I have half modulus q k dot square minus this omega could be different for different oscillators. So, I will put an omega k here and a q k mod square. All right. So, I could have thought of k as 1, 2, 3, 4, infinite number of them, and each one of them has an oscillator and a frequency omega k square, which depends on that oscillator. So, I haven't done anything here. Now, I motivate something, because we had already seen that if you take electromagnetic field, remember that this is some kind of a toy model for electromagnetic field. So, if you take the electromagnetic field is done in the Fourier space labeled by a k, but that k was a vector. So, that is no big deal, I could have made this a vector. So, you take a space of k, kx, ky, kz, every point in that that space has a dynamical variable qk sitting there. It could have been ak. So, at this stage you should be able to connect to electromagnetic field, except for the fact that that would have been a vector, and here I am just using a scalar. Okay. So, you have got that and you are summing over all k. Now, if k is a continuous variable, instead of summing over all k, I would just integrate over all k. So, I put an integral d3k over, let us say, 2 pi d whole cube. This is my Lagrangian for the whole system. So, this just describes harmonic oscillators, innocent, harmless harmonic oscillators. They do not talk to each other, and there are infinite number of them, and they are all labeled by a vector k. What about their energy levels or states or whatever? How will you describe the energy level of that oscillator? That is easy, because the energy level for every oscillator is given by half h cross, if you take one single oscillator, half h cross omega k, and I have to tell you what is the integer corresponding to that, that is nk plus half, and then if there are so many oscillators, I have to integrate over all of them, because I am just summing over all. This will be the energy of that system. If you specify the state of the system by giving these numbers, n for k1, n for k2, n for k3, n for k4, etc., for every k. So, n as a function of k, vector k you have given, then you know it should be integer valued, then you know exactly what is the state of the system, completely specified by this. Good. What is the ground state of this system? That is also easy, because the ground state is going to be the ground state for each oscillator multiplied. So, I wrote down the ground state here. So, if I take, this is the ground state for just x. If I had the ground state for x and ground state for y, I would have got x square plus y square. So, that is mod qk square. So, the ground state for the one of the oscillators was exponential minus half omega k mod qk square. Now, there are several oscillators, so I have to take the ground state for each one of them and multiply them. There is a normalization factor here which we won't worry about. So, I am going to multiply all of them. So, if you multiply a whole lot of exponentials, all the things in this in the argument will add up. So, I have to add up all of them, which is same as integrating in the continuum limit. So, I get proportional to exponential minus integral d3k over 2 pi the whole cubed times this quantity. Okay. So, this is the state of the oscillators, and this is just bunch of oscillators multiplied together, they are not talking to each other. So, this is no big deal compared to one oscillator. Only big deal comes when you want to express these things in real space, not in the Fourier space. So, how do I do that? So, I have got these variables qk, where k was just labeling the oscillator, but since k is a vector, I can define another quantity which I will call phi, which depends on t and x, which is defined by integral over d3k over 2 pi the whole cube qk of t. Qk of course depends on t, because this is the Lagrangian and all that. Okay. So, qk of t e to the I k dot x. This is of course the Fourier transform. I was told that not everyone may be familiar with Fourier transform, but in the first lecture people seems to have generally went along with the lecture. So, I am going to assume that you understand how to do these things. So, this is a quantity which depends on t and x. So, I had some k space in which every point in k there was an oscillator sitting. I just multiplied it by e to the I k dot x and integrated over k, and I found something here. This is good. Now, how do I write qk in terms of phi? That is called the inverse Fourier transform. So, I will just write it down for you. Qk of t is integral over d3x of phi of t comma x with e to the minus I k dot x. If this is plus, you put minus here. So, just to distinguish between these things, let me call this p. So, I have a p and a p. So, if you give me some phi, I can find what qp is. That this implies this and this implies this is coming from Fourier transform. So, if you do not know that, you look that up. So, given any field, this you call a field because it is a function of space and time. So, it depends on space and time, and then you can take a Fourier transform and you get this qp oscillators. And if these oscillators are in a ground state, then the ground state wave function is given by this. Okay. So, everything seems to work out fine so far. And if you give me any configuration, suppose you ask what is the probability that I will have a particular field configuration in the ground state of the system. Well, you give me the field configuration, you give me something like 1 upon cos h of mod x. Okay. So, you give me that function, I will Fourier transform that function, I will find you what this is, then I will go and plug it into this. Then if you know what is this omega k, I can plug it into it and compute a probability. So, you can actually define a probability for a particular field configuration to exist. So, even in the ground state of the harmonic oscillator. All right. How is this possible? This is possible because even in the ground state of a single harmonic oscillator, non-zero values of q can exist. Classically, if the system is in ground state, q is 0. But quantum mechanically, non-zero displacements have a finite probability. Of course, it is a Gaussian, it is peaked and all that, but there is a non-zero probability for a displacement. Each displacement gives you a particular field. So, in the ground state, or what we loosely call vacuum of a field, the field can have different values. So, if you take the vacuum state of the electromagnetic field and say that I want a particular electric field to exist there is a probability for it. These are called vacuum fluctuations. So, in the vacuum there are fields and there is a probability for that, which is no more surprising than the fact that in the ground state of the harmonic oscillator, a 13 centimeter displacement of the basic variable is possible. It need not be sitting just there. Okay. But it is a little bit of a funny thing to sort of call this phi and then work everything with phi and then go back to q to do this. So, it would be nice if we can write everything in terms of phi. For example, can I write down this Lagrangian entirely in terms of phi instead of q? Here it is written down in terms of q. So, can I write it in terms of phi? Actually, you can. The way you do this is the fine. These chalks have some problem or the duster has not worked out. Let me see. Yeah. Okay. So, what I want to do is to express this term and this term in terms of phi. So, let us look at this term first. So, if I take qk dot will be just, I will put a phi dot on this because that is the only thing which depends on time. But I want qk dot mode square. So, qk dot mode square will be two of these things multiplied. So, I have an integral over d3x e to the minus I k dot x phi dot at t comma x. Then I am going to multiply it by integral over d3y e to the minus I k dot y phi dot at t comma y. But the second one is coming with a star. So, let me put a star plus here, and phi I will assume to be real. So, I am not putting a star on phi. So, there is a phi dot. So, this is a phi dot at y, phi dot at x. This is e to the minus I k dot x and this is e to the I plus k dot y. But this quantity is just qk dot square. What I need is qk dot square integrated over k. So, I will just put an integral here. This is integral over d3k over 2 pi the whole cube. So, I have to integrate this quantity over k. What depends on k? This depends on k, this depends on k, nothing else. So, I need to evaluate the integral d3k over 2 pi the whole cubed e to the I k dot y comes with plus sign minus x. Now, this quantity is known as a Dirac delta function. It is equal to delta, it is written as delta of y minus x. Now, if you do not know that, I will give you a rapid introduction to that. How many of you do not know this? 1, 2, 3, etc. But do you people who do not know this know Fourier series and inversion of Fourier series and all that? You do not? Little bit, okay, fine. Okay, so the idea of this is just a generalization of what we know as a Kronecker delta. So, let me just give you a rapid introduction to that. See, suppose I have a function, let me do it at this end, so that it does not affect the flow. So, suppose I have a function which takes discrete values. So, suppose I have a function which depends on two variables n and m, okay, or rather let me actually write it as delta. Suppose you look at this quantity and you multiply it by a function which depends on m and you sum over m. This is Kronecker delta. You think of it as a matrix, just diagonal values equal to unity, everything else 0. And this is a function which depends on m. I could have in fact thought of this as positions in space. There is, let us think of one dimensional space. This is xn, this is xm, and this function depends on, let us say, xm, which is what I called fm. So, if I do that, you know that what you are going to get is just going to be f at xn. Right? Everybody is clear with this. Now, I want to write a continuum version of this. So, this is discrete, I am summing over m. So, instead what I want to say is that integral over dxm, which I will just call dx for the moment, of okay, I do not even need vector symbol, of a function delta which depends on xn and xm. xm I have called x, xn I will call y, y and x, function of x. This should be equal to function of y, the same function at y. So, what have we done? We have just generalized the Kronecker delta to a continuum. What we are saying is that if this function, if this multiplies anything and you integrate over one variable, then you get the value of the function at the other variable. Okay. So, this is a generalization of this quantity Kronecker delta to a continuum thing. Well, strictly speaking, mathematicians will first and say this is not a function, but a distribution, etc., but just think of it as a function, it works. So, you think of this as this is called the Dirac delta function. What I have not proved, which you can look it up in a textbook, is that Dirac delta function can also be written as this. Now, the form of the Dirac delta function is, you think of some Gaussian and you think of it going to narrower and narrower Gaussian, but with the height going to infinity. So, if I look at delta of x as a Dirac delta function, it is infinity at x is equal to 0 and it is 0 everywhere else, with the area under the curve still remaining unity. Okay. So, if you take x not equal to y, or let us first take x is equal to y. If you take x is equal to y, this thing goes away and you are integrating over d3k in an infinite interval. So, it is clear that at x is equal to y, it blows up. For x not equal to y, you have to show that it actually vanishes. That takes more doing and that can be done. Okay. So, this integral here with this d3k is going to give me where is my d3k? Okay, I did not put the d3k on the right hand side. So, this has to be integrated over d3k over 2 pi the whole cube, etc. So, if you do that, this e to the I k dot y k dot x d3k over 2 pi will give me a Dirac delta function. So, this is going to become integral over d3x, integral over d3y, Dirac delta function of x minus y or y minus x. It is an even function, but I might as well write y minus x, y minus x. Then I have the remaining things, phi dot at T x and phi dot at T y. Now, you use the property that if I integrate d3y with y minus x with some function of y, all that rule tells you is that replace this y by x and forget about the integral. So, that integration over, let us say d3y of this delta function, I am integrating over y. So, that means every y has to be replaced by x. So, this is just phi dot square at the same point. So, I get the answer to be phi dot square at t comma x. So, what is the result? The result is that the first term, which is this qk dot square integrated over d3k over 2 pi square, can be written entirely in terms of this phi. All right. Now, the second term requires a little bit of doing. So, it has an omega k square here. So, if I try to repeat exactly the same argument, you will find that I have to integrate omega k square e to the I k dot x and k dot y, and that I cannot do until I know what is omega k square. So, in general I will get some horrible thing. So, the Lagrangian will have one term which is the time derivative square, but then this is going to give me all kinds of spatial dependence. Okay. This is what happens in condensed matter. That is why in condensed matter most of the time they would prefer to work in Fourier space. But there is one particular case where something remarkable happens. So, I want to concentrate on that case. So, this omega k square is some function which we have not specified what it is. The suppose you consider a particular case where this omega k square is a quadratic function of k, that is omega k square I am going to assume has the form k square plus m square, where m is a constant. Why am I doing this? Because I have in the back of the mind using this field to describe relativistic particles. I mean, you can say that it is just an answer, let us see what happens. But I have in the back of the mind using this entire formalism to describe relativistic particle. For relativistic particle, this omega is going to be like energy, because for every particle there is a h cross omega k will be the energy in the kth state, and k is going to be like momentum, because it comes with a e to the I k dot x. Okay. So, you have momentum and energy, and the momentum and energy for a relativistic particle are related by this. So, suppose I plug this in, then the second term will have a k square q k dot square and an m square q k dot square, q k square. M square q k square is trivial. You repeat exactly this calculation, do not put a dot here. So, that k k square that m square q k mod square is just going to give you exactly this without the phi dot square, it will give you phi square. Now, k square q k dot square I am going to leave it to you as an exercise. That is a little tricky, but how can you get a k next to q k? What you do is that you take the gradient of this. So, what is gradient of phi? The gradient operator is going to act on e to the I k dot x. You are taking gradient of this, that is you are taking derivatives with respect to it. Remember, the nabla operator is like I k. So, you will end up getting an I k here. So, these two will combine, that is I k q k is what you are going to get. Then when if you repeat the entire calculation, k square q k square which comes from here will give you from the gradient. It will give you, instead of this, it will be gradient of phi square. That part I want you to work it out. So, if you do that, your Lagrangian is going to be your final Lagrangian is going to be, after you have integrated it over k in this, the first term is what we worked out explicitly. So, it will be d 3 x there is a half which I will keep outside, d 3 x, you are going to get this phi dot square term. Then in that omega square k square, there is going to be one term which is k square, which I told you will give you the gradient square. Then there is an m square which is just going to give you phi square. So, what you are going to get is phi dot square minus gradient of phi mod square minus m square phi square. This is very interesting. Why is it interesting? It is interesting because, forget this term, this is just I could have even put m is equal to 0. This is a term which involves m square and phi square, but the time derivative and spatial derivative appears in a very nice way. Both of them appear together, their derivatives are squared and one is subtracted from the other. So, this tempts one to write the whole thing in a nice relativistic fashion. To do that, we will do the following. Remember that we had this original definition of an event and an infinitesimal variation of the event. Suppose you look at dxa. That dxa was dt and dx. Okay. So, based on that, I can define some general quantity with 4 components. Let me call it say UA or VA, because it need not be velocity or any such thing, V A, which has a component which is V 0 and a vector V. All right. Now, in the case of dxa, we found that there is a nice Lorentz invariant object which is what we call the interval. So, we defined an interval ds square which was c is equal to 1, which was dt square minus dx square. What is dx square? Dx square is dx dotted with dx. Dt also you can think of as dt dotted with dt. If only this was a plus sign, then we would have said this is a dot product of this quantity with this quantity. I mean the dot product of it with itself. The dot product of this will give you dt square, this will give you dx square, and suppose I had dx, dy, dz, then dx square plus dy square plus dz square is just the dot product of that. Here I want to generalize that dot product slightly. In order to do that, it is convenient to define another quantity dx with a subscript which is by definition dt, but with a minus sign in the spatial components. And similarly for any other vector. So, I can define a V A which is this V 0, but with the spatial component changed into minus V. Okay. Then it is there is a very nice way of writing this. You write it as dxa dxa. Remember the old convention suggested by Einstein that whenever an index is repeated, you have to sum over it. What is dxa involved? It has dt and minus dx, that you have to multiply by this dxa which is upper. So, when you multiply, you will first get dt square, then you will get this into this which has a minus sign nicely put in. So, such expressions are Lorentz invariant. That is, in general, if I have one index lower and one index up and I am taking a product of these two, just as ds square does not depend on any Lorentz prime. When you make a Lorentz transformation, it transforms. All these things will transform. This thing will transform just like dt and dx. That is the definition. So, because of which all these quantities, if I write a VA, so if I have a quantity V square defined as VA, that is relativistically invariant and it will not depend on in which frame you are working. Now, I can write this quantity nicely in that form. So, to do that, I have time derivatives and spatial derivatives. So, let me define a quantity which I will call dA of phi, which is by definition just a notation d phi by dxa. Okay, this is just a notation which I am introducing. So, if it is d phi by dxa, it has components which are d phi by dt, which is phi dot, and it has components which are d phi by, this is nabla of phi. So, this has lower index. So, I can also write a quantity, define a quantity with an upper index that would be just like this, but with a minus sign. So, it will be phi dot and minus del phi. So, of course, you could have started with this, think of this as some VA, then the lower index will have the minus sign. Since I already put a minus sign there, it becomes plus. Therefore, the quantity which is phi dot square minus del phi mod square is a vector mode equals just dA of phi dA of phi. That is what I was after. So, this is just like either dxa dxa or va va, and that does not depend on which Lorentz prime you are computing it. So, you can maintain Lorentz invariance with a structure like this, which essentially says that if you have time derivative which is quadratic, you should also have a space derivative which is quadratic with a minus sign. Once you have got that, you can do this. To get this, you have to assume this. Okay. So, once you have all these in place, what is action? Action will be integral over dt of L. So, I had to put an integral over dt as well. So, there is a dt and a d3x, dt, dx, dy, dz. So, I can together write this as a single entity d4x. So, 4-dimensional integration, just like you do 3-dimensional integration. Then I have a half, this half. Then the rest of it we have now found a nice way of writing dA phi dA phi minus m square phi square. Okay. That was a lot of maths. Now, let us look at the physics. We started with 2 oscillators, then made it into a complex oscillator. Then we said let there be more oscillators labeled by QK. So, you have a system which was a bunch of oscillators. Then from this oscillator, I defined for you a field. Have I rubbed it off? No. I have defined for you a field. From the oscillators, we got the field. We originally defined it without that del. Phi is this, and the oscillators are related to this field by this relation. Then I said for the oscillators, I have a Lagrangian and an action. Let me write down this action entirely in terms of this field. Now, then I said that unless I know what is omega k, I can't do these integrations. The most crucial assumption in all the analysis, everything else is mathematics, is that this omega k square is given by this relation. If it is given by this relation, then this Lagrangian can be written in a very nice way, or the action can be written in a very nice way like this. This is called a scalar field, because this is a field and it is a relativistically invariant object, because I have everything written down completely in 4-dimensional notation. There is a d4x integration and this, and I can think of this as a dynamical system. So, I could have started with this. I could have started with this field and then said that let us write phi in terms of q by this relation, plugged it in and then worked out everything. Then I would have arrived at this Lagrangian. Then I would have discovered that the field is nothing but a bunch of harmonic oscillators. This is exactly what we did with electrodynamics. In the electrodynamics, we already knew what equations electromagnetic field satisfied. That was the Maxwell's equations were known to us. So, once you know the Maxwell's equations, we knew what is the dynamical variable, and we found the dynamical variable is a harmonic oscillator. In order to do that, we had to go to the Fourier space. At that time, we hadn't introduced the action, because I did it in the very first lecture. So, as a result of which I did not write down an action, but once I had the harmonic oscillator, I could have written down the action for the harmonic oscillator for an infinite number of harmonic oscillators, and then got the action for the electromagnetic field. So, that is not a big deal. Or I could have started with the action for the electromagnetic field and decomposed them into harmonic oscillator. So, there is this complete equivalence between any non-interacting field and a bunch of harmonic oscillators. But what does it buy you? Where does it connect up with a relativistic particle which was going up and down, etc.? What it buys you is the following. Suppose I quantize this scalar field. Suppose somebody has given me this classical field with that Lagrangian, and you have classical equations, you have the action. So, you can write exponential I times action sum over all configurations, and then you can try to find out what is the dynamical evolution of this field described by quantum mechanics. This is completely equivalent to the dynamical evolution of a bunch of harmonic oscillators. Therefore, if you can write down the Schrodinger equation for any one of those oscillators, then you have the Schrodinger equation for this field. So, you decompose them into harmonic oscillators and write Schrodinger equation for each of the oscillators. So, you know what is the quantum state of the field as a product of the quantum state of the oscillators. In particular, let us consider the states with fixed energy. So, a state with a given energy is specified by a bunch of integers, because every oscillator has to be given an integer n. So, n of k, for every k you give me an integer, then that defines for me the state. Again, completely simple. I mean, if you know one oscillator, you can do quantum field theory. So, the quantum state of the system is described by these harmonic oscillators. And in particular, you can also look at the ground state. So, let me do that. That is quite nice to illustrate this concept. So, I wrote down the ground state here. Okay. So, this ground state I would like to express in terms of the phi, because this is expressed in terms of qk square. So, I want to express it in terms of phi. How do I do that? I will take the simplest possible case. I mean, you can work it out more complicated cases, like electromagnetism, for example, will correspond to this dispersion relation with m is equal to 0. Remember, we found that the harmonic oscillators have frequencies which has k square c square. So, the m was 0 there. So, let us take the m is equal to 0 case. Then the integral which I have to perform there is given by integral over all the oscillators d3k over 2 pi the whole cubed. There is a fact. Then I have an omega k, which is just modulus of k, because we are taking m is equal to 0, modulus of k into qk square. So, I will write this as modulus of k the whole square upon modulus of k. This is just modulus of k, is just a trick. Then you have mod qk square. This is what you have. But k square, this qk square can be pulled off from this. We know that ik qk is the Fourier transform of this gradient, because once I take the e to the ik dot x and put it here, I get the Fourier transform of that. Therefore, if you work this out, which is again going to be left as an exercise, what you will find is that this has an expression. There are some numerical constants here like 4 pi etc., which I will not bother about. This will become a nice expression d3x d3y gradient of phi evaluated at x. So, I will just put x all at a given time, gradient of phi evaluated at y upon mod x minus y the whole square. Actually, those of you who are quite familiar with Fourier transform should be able to actually see it in a glance. If there was no this k, then this is just equal to the top quantity, because that we have done hundreds of times now. This 1 upon k tells you that you have to take the Fourier transform of e to the ik dot x upon k, and that Fourier transform is 1 by x square. Okay. So, you should actually sit and dirty your paper and pencil a little bit and work that out. So, this is a good exercise. It's a fairly simple exercise, but a good exercise. Figure out what this constant is. As I said, it only involves 4 pi's and things like that. But what does it mean? What does this expression mean? Let me call this expression some quantity q. Okay. Then it tells you that the ground state of this system which you say has no particles, depends on the field as there are constants which we do not care, exponential minus q. This is an extremely physical statement. What it tells you is that take the vacuum state of the field and suppose I want to find a particular field fluctuation in that field. That field fluctuation is given by a function phi of x. What is the probability to find that? Or rather, suppose somebody, because there are constants, you can take relative probability. You take one field fluctuation and another field fluctuation, and you want to know what is the probability to do this. This is exactly like you will learn in quantum mechanics, that if I have a harmonic oscillator, what is the probability that the particle is displaced by 13 centimeters versus 45 centimeters in the ground state. So, the ground state is e to the minus some q square. You put 14 and then you put 45, and the ratio between them will tell you what is the relative probability. Here you are given not a displacement but a function, how the field is fluctuating in space. So, once you know that function, you know what these two gradients are, you take this dot product, you divide by x minus y the whole square and you integrate, you get a pure number 43, and exponential minus 43 is the amplitude for a probability, I mean mode square of this will be the probability for that field fluctuation to exist. So, this is exactly what people call the vacuum fluctuation. If you do this for electromagnetic field, which is identical, and you will end up getting an expression which involve magnetic field at one point and magnetic field at another point, which are the dynamical variables, divided by actually x minus y the whole square. So, if in the vacuum you want to measure a particular magnetic field or a particular electric field, you can write down the expression like this. But what we are really interested in is not so much as the vacuum state, but the particles or the excitations of that. So, suppose you take the first excited state of the field. What would be the first excited state? So, let us try to label the states. The vacuum state will correspond to 0, 0, 0 for every oscillator. Of course, there are continuum infinity of oscillators, but let us just think figuratively. They are all labeled by a vector k. So, this is the kth oscillator, let us say. Now, suppose I go to a state which is 0, 0 and I put 1 here. Everything else is 0. So, I have all the oscillators in the ground state, one particular oscillator has jumped to the first excited state. So, what will be the energy of this state? The energy of this state will be just this expression with h cross omega k, and here there is a 1 and there is a 0 point energy. So, let us decide to measure everything from the 0 point energy, that is, we will ignore this half for a moment. So, the change in energy is h cross omega k times 1. So, the moment you have excited it, a quanta of energy of amount h cross omega k has been either absorbed or emitted. Now, you excite it twice, 2 times that. So, the oscillators, because it is evenly spaced, suppose I have nk in the kth for the kth oscillator, the energy is actually going to be nk times h cross omega k. This is the contribution from the kth oscillator to the total energy when it is in a state nk. But that is like particles. This h cross omega k, you can also write it in using that expression which we had. Where is it? Here. It is h cross square root of k square plus m square. The constants will adjust themselves. If you take h cross inside it, this h cross square k square will be p square, and this m actually has an 1 upon h cross and c, and they will all take care of themselves. So, it is much nicer to think with the h cross equals 1. So, yeah. Right.
We can see the excitation.
Correct.
Like we have one photon and a harmonic oscillator in excited state.
That's right.
But if you look at this file, then how can we see this excitation?
You cannot. You simply cannot. So, even the ground state, which you can think of as nk equal to 0, that is, there are no excitations, has excitations in the field, because any field configuration can exist in the vacuum. So, this is exactly what happens for a single harmonic oscillator. Suppose I am looking at the harmonic oscillator as a function of q. Okay? Take the ground state or the first excited state. It will have some kind of a profile. There is a particular probability for it to have a particular displacement. Now I ask you whether it is in the first excited state or in the ground state, etc. Without taking a Fourier transform and expanding it in terms of these states, you cannot tell me. Because even the ground state with no excitations contains non-zero probability for a non-zero displacement. Therefore, that is why the Fourier picture is extremely useful in quantum field theory. These excitations live in Fourier space. They are labeled by a momentum k and they are labeled by the energy omega k. So, when you change k, when you change nk, okay. So, I can have nk for different k's. So, every time I change nk, you are either adding particles to the system or removing particles from the system. So, if this oscillators, this bunch of oscillators is interacting with something else, like if there is an electromagnetic field and it is interacting with some other radiation, with some charged particles, then what will happen is that it will induce excitations between these states. The kth oscillator can go from n is equal to 2 to n is equal to 4. What you will say is that a photon has been absorbed or emitted in the process. And that photon has an energy which is h cross omega k. There were nk of these photons which were milling around. So, the state of the system is described by number of particles with momentum k. So, you tell me that, then I know what the state of the system is, except for the ground state, which all n is equal to 0. And then the excitations come. The crucial point here, actually two crucial points. One is this dispersion relation which we put in by hand. That is why these particles have the correct relationship for a relativistic particle. E square and p square is related by E square equals p square plus m square. The second important point is that harmonic oscillator has evenly spaced energy levels. That is why when the whole bunch of harmonic oscillators are labeled by these nks, the total energy of this system, which will be the sum over all k, let me resort to a summation notation here, will be like this. This is exactly what you will get if I take nk particles with energy h cross omega k and dump it together. So, whether you want to think in terms of excitations of the field or excitations of the harmonic oscillator is purely a question of your personal preference. Mathematics remains the same. Okay. So, this is how we describe our relativistic particle. You start with a field and then you write down the how the field is going to evolve, and then you decompose the field into harmonic oscillators, and the harmonic oscillators have ground state and excited states, and they get labeled by the integers, and these quanta are the particles. Now, everything which I have said remains true even if this dispersion relation is not this. If it is not this, you won't have Lorentz invariant, you won't have a quantum field theory. But in condensed matter, this is what you do. Suppose there are some excitations, some phonons or rotons or whatever. There, the relationship between omega and k can be much more complicated because of all kinds of reasons. But these various phonons, rotons, etc., given that excitation, you have a picture in harmonic in the Fourier space in terms of harmonic oscillators, and you can talk about the systems which contain certain number of excitation. After that, when you switch on interactions, all this is free field, free electromagnetic field, etc. When you switch on interaction, these oscillators get coupled. The kth oscillator can talk to pth oscillator, and that will be described in terms of emission and absorption of these quanta. Okay. So, that is all which I wanted to do as far as the fields and their representation and particles. In remaining half an hour, I want to derive for you one more action. So, we did action for a free particle, relativistic free particle, and we also did action for a particle in a gravitational field. I want to get you action in an electromagnetic field. Now, the electromagnetic field itself I have not introduced, but we want to see how that can be introduced and how the action can come. So, in order to do that, let me go back to the nature of the action for a free particle which we introduced. what we did was that we set the action xf for a constant, and that constant we finally fixed in terms of mass is integral ds. You remember this, right? We did it long back. And this ds was square root of some eta ab dxa dxb or gab dxa dxb. That gab is what gave you how the gravitational field affects this particle and all that. Now, this is first order in ds, which was obtained by taking square root of dx square, so to speak, right. That is a very complicated way to get a linear term. Why not just put dx? So, I want to add another term, I mean try thinking in terms of another term. There is another constant here like m, and I just want to put something like dxa. Instead of ds, I want something linear in the length, because we said that it is like a length. So, why not put just dxa? Well, the trouble is this is not a scalar quantity, it depends on a, there is an index sitting there. So, there are 4 quantities here. So, we want to eliminate that, but by now we know the trick for that. If you have a VA sticking somewhere, if I multiply it by something with a lower index, it need not be the same VA, it could be some UA, then you get a scalar. So, let us go and multiply this, I will put index I by another vector which I will call with a lower index, which I will call AI. Okay. So, this AI can depend on space and time. So, it is a function of t and x. Now, we want to know what kind of system this action describes, as simple as that. I mean, you had a ds, I just wanted to add another term which is linear in xi. So, to understand what kind of system this action describes, I will also make action calligraphic, so that not to confuse with that a. We want to calculate delta A is equal to 0. This is going to be a bit of a computation, but let me try to take you through that. So, what happens is that you want to do delta of A, this is minus m integral, I had to do a delta of ds. Remember that this ds was actually square root of dxa dxa. So, I am doing a delta on that. So, delta of a square root will give me half, then I will get the square root in the denominator, which is just ds, I will write it again as ds. Then I am going to do a delta on this, there are 2 terms, so that will give me a factor 2 which will cancel with this, 2 times delta of any one of them. So, I will write it as dxa, delta of dxa, that I will write as d of delta xa, because they commute. This is the first term. Now, let us look at the second term, that is minus q, I will probably need more space. So, minus q integral delta of this whole quantity. Okay. So, delta of this whole quantity is, first I have d of delta xi ai, then I will get minus q integral dxi delta of ai. Okay. So, I have a delta of ai. What is delta of ai? Here is where all the gymnastics with the indices come about. Delta of ai is change in ai when the path is varied. So, the path comes with a index some xj or something. So, you want to compute the derivative of this with respect to, let us say, xj delta of xj. Then let us look at this quantity. This quantity is some d of this delta xi times ai. So, I have to take this is d of delta xi times ai. So, this I will write as d of delta xi ai minus delta xi d of ai. D of ai is again d of ai upon, let us say, dxk dxk. This is pretty heavy algebra, but I am assuming that you are following me step by step. So, we have got all of them in some shape, and let us try to clean it up a bit. So, in the first case I have this quantity, and that also that we know how to do so by now, hopefully. So, this is dxa by ds and a d of delta xa. So, we again write this as d of that whole thing dxa by ds and delta xi minus d acting on this quantity d of, let me call this dxa by ds for convenience as a quantity ua. So, it is minus d ua okay, this a should have been upper d ua delta xa. Okay, now we have to make sense out of it. So, let us write down the terms one by one. Delta A, the action, is going to give me here two terms. There is first a d of this ua, I can write it explicitly, ua delta xa, that is going to be integrated. So, it is going to contribute only at the limits, and in the limit delta xa is going to go to 0. So, this does not contribute. So, the term which I am going to get there is plus m integral, this minus sign and this minus sign gives me plus m, then there is a dua delta xa. I write this as dua by ds delta xa ds. So, that is fine, it is an integral of some quantity times this. Now, you can also figure out what that quantity is roughly. Dxa, xa is like coordinate, so dx, s is like proper time. So, dxa by ds is like the velocity generalized into 4 dimensions, it is called 4 velocity. So, one more derivative of that is 4 acceleration. So, that is what you have. Good. Now, let us look at the other two terms. Then I have this term which is going to give me minus q with an integral. So, here again there is a d of delta xi integrated over this. So, when I integrate all over, it only contributes in the boundary, and the boundary delta xi is 0. So, this does not contribute, I only have to worry about this term. So, that term I will again write as dxk by ds into ds, and dxk by ds is what I have been calling uk. So, this is uk ds. Okay. And this term again I can write it as dxi by ds into ds, and take this dxi by ds as ui. Well, of course, if I make an algebraic error, finally we will correct ui. So, these are the only two terms which survive, so which I want to retain. So, minus q I have taken out. So, I have a term which is ui dxi by dai by dxa, which I will condense the notation a bit, and I will call it dj of ai. Then I have a delta xj and a ds. delta xj and a ds. Then I have one more term coming from this. So, I had to get the signs right. This is minus q and that was this, okay, I wrote down this term which is fine, and then I have this term which has this minus that is going to become plus. So, I get a plus q. Let us see what that has. That has a UK, then it has a decay of AI, and I have a delta xi ds. You are almost there, just grit your teeth for some more time. So, you have got this final expression here. Now, what we want to do is to combine these two. Now, this has dxj, this has dxi, and this has an I index floating around here. So, we will play a trick. This I index is summed over, right? So, I can replace it by any index I like. So, let me replace it by L. And here also there is an I index which is summed over. So, let me replace it by J. So, by this trick I have got delta xj in both, that is good. Then here this is dk and j, this is j and L. It would be nice to get an L here. So, let us replace this k by L. Very good. So, what does it give you? It gives you that the quantity inside, I have an integral, then I have a ds, and I want delta xj everywhere. So, I will put this also as j and this also as j. So, I have a ds, then I have a delta xj in all the integrals, and I put a big curly bracket. So, I have a m, then I have a, yeah, I should have kept m inside. Okay. So, there is a delta xj and a ds I have taken out, then I have a m duj by ds, that is in the first term. Then I get, I want to take these things, dxj ds is outside, so I do not have to worry about that. Then I have a q, so let us take minus q out first. Then I have a ul, ul is also common, ul is there and ul is there. What multiplies it is that here I have dj of al minus, here I have a dl of aj. And now we can close the bracket. This is a beautiful result. So, all that I did was I wanted a linear term axi. Now, I can't have just a linear term. So, I wanted to add something here which is like a 4 vector. So, I just threw in an ai and I said this ai depends on all the coordinates. Then I said let me just see what kind of equations of motion that gives. Okay. So, what is the Euler-Lagrange equation? Instead of taking Euler function and differentiating and all that, I just said let us look at the Euler-Lagrange equation by actually varying. Then it tells you that this is the answer, and the equations of motion you get is that this quantity should be 0. So, this quantity has this weird combination here, which I will call f j l. This is the definition of this quantity. Fjl is dj of al minus dl of aj. Okay? Then you find that your equations of motion are, after removing all this, the equations of motion for your system is m d uj by ds, this is like mass into acceleration, equals q ul f j l. What is this system? So, you have added some AI and you have done this manipulation and you found a force law. It tells you how the particle is going to move under the force which is decided by this UL times FJL, where FJL is given by this. It turns out that this is just electromagnetism, and what you have written down here is just Lorentz force. So, how do you find that out? You try to look at AI. What you do is that you define AI with upper index as the combination of your scalar potential and vector potential. Suppose you do this, then your AI with lower things index will be phi minus A. Now, let us compute any one of these components. So, let us look at f j l, let us call it 0 1, f 0 1, what is it? So, this tensor is just a fancy notation, ultimately it is the numbers which you have to compute. So, f 0 1 will be d 0 of a 1 minus d 1 of a 0. What is this? d 0 is time derivative. What is a 1? A 1 is going to be 1 here, that is a x. So, this is time derivative of a x minus this is dx of a 0, which is phi. You should be able to recognize this, because this is just nothing but minus the electric field along the x direction. Okay. So, in each one of these computations, the three components, this f01, f02 and f03 will turn out to be the electric fields Ex, Ey, Ez. How many components does this FJL has? So, let me just do that for you. If you take FJL, is defined by this quantity. So, if J and L are equal, then dJ of AL minus DL of dJ is equal to 0. So, the diagonal components are 0. If this is 4 index, so there are total 16 components, 4 into 4, out of which diagonal components go away, 4 gone. So, there are 12 components and it is anti-symmetric, that is, if FJL is replaced by FLJ, just sign flip. So, there are 6 independent components. Electric and magnetic field together has 6 independent components. So, what you will find is that here there are F0 alpha kind of components, where alpha is a spatial index, and you have F alpha beta kind of components. They will roughly, except for signs etc., they will correspond to electric field alpha and magnetic field in some direction. So, which you can work out if you really want to. So, if you look at this particular object and you take a particle which, for example, is at rest. So, what does that mean? If a particle is at rest, then if you compute dxa by, for its 4 velocity ua, if you compute dxa by ds, particle is at rest. So, spatial components are all going to be 0. And time component is going to give you 1, because your dt is same as ds. So, if you have such a particle which is at rest, only u1 will contribute, u0 will contribute. So, there is only a 0 here, because this 0 will sum over only 0, and then this j can take any value it like except 0. So, if j takes 1, 2, 3, let us take 1. Then it says du1 by ds, which is the acceleration along the direction 1, is given by the electric field E times q, because the other one is 1. It requires a little bit more work to get the magnetic field thing, that it is V cross B, but I will leave it at that. Interested people can take it further. So, I wanted to give you this example just to show the simplicity. I mean, forget all the algebraic complication, just to show the simplicity that how, because people were asking right at the beginning that, oh, what is an action and how do you know the dynamical variables, etc. The way you discover actions is by using symmetries. So, you have ds, which was Lorentz invariant, then you ask what is the next simplest thing you can do, which is Lorentz invariant. The next simplest thing you can do is electromagnetism. So, this is why I said early in the lecture that electromagnetism is best thought of as an offshoot of special relativity. So, once you have got special relativity and you are writing down actions which are invariant under Lorentz transformation, you have ds, then you say I want dxi, then you say that, oh, I do not have anything to hit it with. So, let us postulate or imagine that there is an ai. So, you write down that ai and you ask how the particle moves in this, and you find that it moves in a way which agrees with nature, which is q into E plus V cross B. So, you can actually discover electromagnetism in this process. Let me also make one comment which I promised to make about gauge invariance and gauge transformations and all that. Suppose you take ai, you have some ai and you change it into another ai, which is ai plus di, which is d by dxi of some function f. Okay. So, I have just added a function. So, look at what that second term does here. The second term is dxi di of f integrated. So, this is derivative with respect to xi multiplied by xi integrated. So, this is only going to give you contribution at the endpoints. Now, we learned long back that if you add to a Lagrangian something only gives contributions at the endpoint. If you are fixing things at the endpoint, this is not going to affect your equations of motion. That is in fact easy to see. If you take this definition and you take two a's which differ like this and you compute fjl for both of them, you will find that fjl for the Barth quantity is the same as fjl for this quantity. So, the electric and magnetic fields do not change when you do this. So, you can use this freedom to set ai to restrict the form of the ai to a certain extent. That is what we use to set that divergence of a is equal to 0 and phi is equal to 0. Again, the gauge transformation looks very mysterious when you look at it in the three-dimensional language. You have E and B and then I can add this and subtract this and all that, it works out. But in the when you do this, I mean same philosophy, exact theories are more beautiful than approximate theories. In an exact theory, electromagnetism is just ai times a dxi, that is all. And if ai added to a di of phi does not change the action and it does not change your equations of motion, then it is a perfectly good invariance, and that is called the gauge invariance of the theory. Okay. So, I wish I had one more hour to fill up various details about it. That has to be next year. Thank you, and I will take questions. So, since this is the last lecture, anything you have in the earlier classes also, if you have something, you bring it up. Any questions?
Sir, about the Schwinger interpretation of the
Right.
that there are multiple, instead of having multiple particles in all the fields,
Right.
you can think of a single particle.
Right.
So, physically, if we think about these two interpretations, they seem to be very different.
That's correct.
So, how can we work in that interpretation and
Yeah. So, nobody has a very clear idea as to physically how to interpret Schwinger's formalism, because even with that you cannot write down wave functions and things like that. But mathematically it is a very nice way, because what you are doing is actually counting these paths which are going up and down, and in the Schunger's interpretation they are naturally incorporated. So if you are doing computations, I mean Schwinger has an entire formulation of quantum field theory which is sort of different to the standard formulation, in which he works out everything in standard formulation using his approach, and everything comes out right, and most of the time the calculations are simpler. Okay. So mathematically it is a good technique, but physically even in this interpretation it is just an intuitive picture. We know that we are thinking of particle, I mean how do you interpret a particle going backward in time? It's just a way of talking, but that way of talking allows you to compute things which are observable in a very nice way in Feynman diagrams and things like that. So both these methods have their own limitations, in the sense that direct physical interpretation for the virtual processes is difficult to come by, and depending on the context you should choose either or not. Any other question? Okay, thanks.
Thanks, Paddy, for the series of